Today we are solving LeetCode 1343. Number of subarrays of size k and average greater than or equal to threshold. This problem teaches four important DSA concepts: fixed size sliding window, reusing a previous calculation, converting an average condition into a sum condition, reducing an O(n) into k solution to O(n). We are given an integer array ARR, an integer k, an integer threshold. We need to count how many contiguous subarrays have exactly k elements and have an average greater than or equal to threshold. So for example, when our ARR equals this value 4 times 2, 3 times 5 and 1 times 8, and k equals 3 and threshold equals 4. The valid subarrays are these 2, 5, 5, 5, 5, and 5, 5, 8, because they have average equal to 4, 5 and 6 respectively. Therefore the answer is 3. Now there is one important observation. For an array of size k, average equals window sum divided by k, and we need average greater than or equal to threshold. So that means window sum greater than equal to threshold multiplied by k. K is greater than 0. So therefore we do not need to calculate the average. We only need to check the sum. If the window sum is greater than equal to this new value called as k star threshold, then we are done. That is the correct subarray. We can increase our count. So this also avoids unnecessary floating point calculations. Now let's discuss brute force approach. So we can generate every array of size k. So this is brute force. We can generate every array of size k, and for each starting index, how we do that? We start for each starting index. We calculate the sum of the next k elements. Then check whether the sum is at least k star threshold or not. Increment the answer if the condition is satisfied. So we can write the code for this brute force. So let's initialize by count equals 0. Then our required sum will be k star threshold. Then we start the loop for start in range length of array minus k plus 1. Window sum will be 0. Then from we run one more loop inside that for the next k elements. For index in range start to start plus k, we keep on adding the window sum. And if our window sum is greater than or equal to required sum, then we increase the count. And finally we return the value of count. So this is a very simple brute force approach. Let us try to test it. So it passes. Now let's discuss its time complexity. So time will be of order and multiply by k, because we are for every starting position we calculate the sum of k elements. We go through k elements for every starting position, and that means starting position can be of order n, and the elements are k. So for each element we are checking k times. K operations are being done. That's why time complexity is order of n star k, and space will be order of O of 1, because we don't need any extra array. We just need a few variables. But this can become slow because our constraint is that the length of array can be between 1 to 10 power 5. It can be as large as 10 power 5. So we need an optimal approach. So let's move on to optimal approach. So this is the fixed size sliding window. We'll create a sliding window of fixed size. The size of every subarray is fixed at k. Suppose the current window is this, from A double R left to right. This is my current window. When we move the window one step forward, remove the element leaving the window and add the new element entering the window. Instead of calculating the entire sum again, we update it using this formula. Window sum will become will minus equals window sum equals window sum minus A double R right minus k. That is the leftmost element that has been removed, and we add the rightmost element. Window sum plus equals A double R right. This is the fixed size sliding window technique. Now let's write its pseudocode. Required sum equals k star threshold. Calculate the sum of the first k elements. Then initialize count equals 0. Then if first window sum is greater than equal to required sum, then count plus equals 1. Now for right from k to end of array, we add A double R right to window sum and remove the leftmost element from the window sum, A double R right minus k. Now we check if window sum is greater than equal to required sum, we increase the count. And finally return the count. So that is the pseudo code. Now let us write the Python code. So let's delete the brute force approach. So let us initialize the required sum, window sum, and the count. Then we check if window sum is greater than equal to required sum, we increase count plus equals 1. Now we'll check for right in the range in the array. We scan the array. If window sum, uh, we keep on including one element in the window, and we keep on checking the condition. If the condition is true, then we increase the count by 1, and finally we return the count. So let us dry run this code for these values. This dry run will give you a better understanding of the code. So first we calculate the minimum required sum. So required sum equals k into threshold. that is equal to 3 multiplied by 4 equals 12. So now process every window. So first 2 to 2. First window will become 2 comma 2 comma 2. So it is sum equals 6 less than 12. So count will remain as 0. Then next window will become 2 comma 2 comma 2. Here sum equals 6 and count equals 0. Sum equals 6, that is less than 12. Count equals 0. Now our next window will become 2 comma 2 comma 5 and sum equals 9, again less than 12, so count equals 0. Next window will become 2 comma 5 comma 5. Sum will be equals 12, so it is greater than equal to 12, so count equals 1. Now next window will become 5 comma 5 comma 5 and sum equals 15, that is greater than equal to 12, and count equals 2, increases by 1. The next window is 5 comma 5 comma 8. Sum equals 18, greater than equal to 12, and count equals. So now no other windows left, so answer equals 3. So this is our final answer. Suppose the current window is 2 to 5. Its sum is 9. To move to the next window, we remove the outgoing 2 and add incoming 5. So new sum becomes 9 minus 2 plus 5. Let me write it down just to show you how the window is updated. So current window is its sum equals 9. Now to move to the next window, we remove the outgoing 2 and add incoming 5. So new sum becomes 9 minus 2 plus 5 equals 12. We update the sum in constant time instead of adding all the 3 elements again. Okay, so time complexity for this, it becomes On, because calculating the first window takes OK and sliding through the remaining array takes On minus K. Therefore On. Space complexity is O1 because we only store window sum, required sum and count. Let us run the code and try to submit it and see if we have got the correct result or not. Let me comment out the logic that we discussed. Let's try to test the code. Okay, accepted. Now we can submit it. So all the test cases pass. Now finally let us discuss the critical mistakes. First mistake is checking every possible subarray size. The problem asks only for subarray of exactly size k, so use a fixed size window. Second mistake is recalculating every window sum. Calculating the complete sum for every window results in O and star k. Reuse the previous window sum instead. Third is calculating floating point averages. This works window sum by k greater than equal to threshold, but this is simpler. That window sum is greater than equal to k star threshold. Fourth mistake is removing the wrong element. When right enters the window, the outgoing element is a double r right minus k. And fifth mistake is forgetting to check the first window. The loop starts from index k. Only the loop starting from index k only processes subsequent windows. The first window must be checked separately. So we can also build the window dynamically, like in which the first and subsequent windows are handled inside one loop that you can code on your own. So the key idea is to recognize that every required subarray has a fixed size. Instead of calculating each window independently, calculate the first window sum. Then remove the outgoing element, add the incoming element. Compare the sum with k star window, k star threshold. This gives us an efficient O(n) time over extra space solution using a fixed size sliding window.